In this video, we'll take a look at vector analysis, how to take vectors that are in two dimensions and find a resultant or net vector, and how to take a single vector and an angle and break it down into its x and y components. Two-dimensional motion happens whenever there's motion on both the horizontal and the vertical axis happening simultaneously. When we start physics, we deal with one-dimensional motion that occurs either on the x or the y axis. So think back to kinematics. When we started off, we were dealing with nothing but horizontal motion. Things are either moving to the left or the right. Then we add free fall, where things are either moving up or down. Everything was confined to a single axis on a coordinate plane. In two-dimensional motion, you have both vertical and horizontal motion happening at the same time. Something is moving to the right and up simultaneously. Something is moving to the left and down simultaneously. This is two-dimensional motion. In cases like these, we use vector analysis to find either a resultant or component vectors. We'll start with resultants. Resultants are vectors that are the sum of all the individual components that an object is undergoing. Think of it as a net vector. So let's say we're moving 10 meters to the right and 6 meters up. We have two components of motion there, a component to the right and a component that's up. The resultant vector would be the sum of those two. It would be some diagonal vector that is up and to the right. That's what resultants are. The vertical and the horizontal vectors are combined together to find a single vector that more accurately describes the displacement of that object in this case. Components are when you take an angled vector and break it down into its x and y, or its horizontal and vertical parts. So again, we can talk about motion, we can talk about velocity, for example. If an object is moving 30 meters per second up and to the right, we know there's going to be a part of that motion that takes it to the right, and there's going to be a part of that motion that takes it upward. When we break it down into what specifically that motion to the right is and what that motion upward is, we're breaking it down into its component vectors. So again, a resultant is when we have two vectors acting in two different directions. So again, we could be going to the east 10 meters and then going north 3 meters. The resultant would be that summary that tells us we moved up and to the right, this dashed arrow that I just drew in. That would be the resultant. It's a more accurate representation of what the true displacement of that object was. We started here, we ended there, how far away from the starting position we've moved. When you're doing components, it's backwards. We moved up and to the right. So the components would be how far to the right I've gone, this arrow, and how far up I've gone, that arrow. Those two dashed arrows would be the components. And it tells us how far in the horizontal I've gone, how far in the vertical I've gone. So they're kind of the opposite of one another. Finding either resultants or component vectors can be done one of two ways. There's a graphical method and there's a mathematical method of doing it. And the graphical, as the name suggests, involves making drawings, more specifically scale drawings of each of your vectors, and using tools like rulers and protractors and coordinate planes to figure out what the magnitude and the direction of your resultant or your components are. And that's where we're going to start with this graphical analysis method. And we're going to do it because you should be able to do this. It's part of standards in high school physics. But honestly, once you learn the mathematical method, you'll never go back to doing things graphically again. It's just much quicker, much easier, and gives you much more accurate results. So let's start with graphical analysis for resultants. When we have the two vectors, one in the horizontal, one in the vertical, that we are going to combine together to find that net, to find that overall or resulting vector. First, in some cases, you will have to start by simplifying all the vectors that are in your problem down to just two. You might have 3, 4, 5 different components in the question, but using two-dimensional vector analysis, adding the ones together in the same direction, subtracting the ones that are in the opposite direction, you should be able to simplify your vectors down into a single horizontal and a single vertical component. So make sure you have just two vectors before you start graphical analysis. It'll make your life so much easier. You can technically do it with 17 individual vectors, but you're going to have a mess of a drawing and you're going to have more opportunities for mistakes as you go. Each individual vector you draw has a certain amount of error that's built into it. You have to use a ruler. You have to draw the length just right. You have to connect them together perfectly. So if you're drawing a graphical analysis of 5 different vectors, you have 5 opportunities to introduce error into your drawing. We want to minimize that as much as possible. So if you have 5 vectors, you'll be able to simplify them down to just 2. There should be one single horizontal vector when you're done. There should be one single vertical vector when you're done. The 2 vectors are then drawn tip to tail, with the first one starting at the origin of the coordinate plane. Now, it doesn't matter which one you start with. You can start with the horizontal vector or you can start with the vertical vector. Doesn't matter. It's probably better to start with the horizontal because it may give you an easier angle to figure out when you're said and done. Easier way to describe what the actual angle of your resultant is. So oftentimes the horizontal is the better place to start, but you don't have to. You can start with either the vertical or the horizontal. You'll get the same answer every single time. The beginning and end of the drawing are connected together. So once you've drawn your 2 vectors, one horizontally, one vertically, you'll connect the beginning and the end of the vector just like I did on the previous page. That vector that you draw in, that third one that you add to complete the triangle, is the resultant. It's that net or overall vector that better summarizes the motion of the object. To make it clear, we're going to do an example here. A boat crosses a river. The boat's velocity is 4.5 meters per second to the north, while the river flows 2.9 meters per second to the east. What's the net velocity of the boat? So this is a case where the net or resultant is much more valuable information than each of those individual components. As the boat's traveling 4.5 meters per second, we know it's not going to end up exactly at the same spot on the other side of the riverbank. The river's actually going to push that boat to the east as it travels. The resultant will give us a better indication of where that boat's actually going to land on the other side of the river. So very useful, very helpful information here. Now you'll see the first thing I did was establish a scale. 1 centimeter is going to be equal to 1 meter per second. And I chose that scale just based on the size of my coordinate plane here. My biggest number is 4.5 meters per second. A 4.5 centimeter line would be this long, and I want to make sure that that's going to fit on my coordinates. I wouldn't want to do 1 centimeter equals half a meter per second or 0.5 meters per second because I know that would take me way off my grid. I don't want to do 1 centimeter equals 5 meters per second because all of my lines would be tiny little things down here, and I wouldn't get a very good drawing. I do want to try to fill in my coordinate plane as much as possible. I want to make as big a drawing as I can because the bigger the drawing I make, the more accurate my results are going to be. I just want to confine it though. I want to keep it inside this coordinate plane. So I'm going to start by drawing out the individual vectors and again connecting them tip to tail. It doesn't matter which one you start with. Oftentimes though, it's easier to start with the one that's going to end up on the x-axis, the horizontal one, which would be the 2.9 meters per second to the east. It's going to go down here somewhere. So that's probably the better one to start with. According to my scale, I need to make a 2.9 centimeter long arrow. Now, in an app like this, it's really easy to do. I've got arrow drawing tools that I can use, but you're going to have to do this stuff on paper. So you're going to have to lay down a ruler on that x-axis. You're going to have to draw an arrow that is very close to the correct length. you're going to have to make sure that is as horizontal as you can make it. Just notice there I made that the wrong length. I went to 3.9, so 2.9. Do that again. There we go. Right there. So this app makes it fairly easy for me to draw these arrows in. And I probably should have used a different color there. Let me see if I can change that to something easier to see. There we go. And just laid that in on the x-axis, starting there at the origin. Now I got to do my vertical one. It's north, so it's going to go upward from here. And it's got to be 4.5 centimeters long. So again, I'm going to start by doing my arrow. 4.5 centimeters. And I should make this a color that'll be easy to see on this too. Let's make it yellow. 4.5 goes to right there. Take that vector, turn it vertical. And again, we want to get as close to vertical as possible. That's why grids like this are very, very helpful. If we're off on either how vertical or how horizontal our vectors are, then that's going to throw off the length of the resultant. And I want that to start right where my last arrow ended, tip to tail. You connect the tip of your first arrow to the tail of your second one. So those are the two vectors. Again, if there had been 3 or 4 in here, I would have combined them together and got down to just 2. I only had 2 in this one to begin with, so I didn't have to worry too much about that. Now I need to connect this from where I started to where my drawing ends, right, like that. That dashed red arrow that I put in there is the resultant. Now to figure out what that is, I have to actually measure it and its angle. So I'm going to go ahead and just start with the angle first before I move this thing. And that looks to be about 57 degrees. Again, this is where how you draw it might become important. We want to think about these things in terms of a standard angle, thinking about this thing as a unit circle, with this being 0, that being 90, this being 180, that being 270. That is a legitimate 57-degree angle. If I had been doing the angle over here, which is what I would have got if I had done the yellow one first and then the green one, my resultant would have been the same length and my magnitude would have been the same, but I would have been measuring this angle over here most likely. And I would have to recognize that it would be 90 minus whatever that angle is. So again, it's kind of important which direction you draw them, because it could make your life easier in the end. As far as the length is going to be concerned, I'm just going to grab this arrow and I'm going to move it to my ruler since my ruler is showing up behind my grid. I need to bring my arrow over here. I need to get it as horizontal as possible so I can measure its length. And that length is a little bit beyond 5.2, so maybe 5.25. And that's meters per second because that's what we were dealing with at an angle of 57 degrees. That is how you do graphical analysis. And it's kind of time consuming. I think it takes a lot longer to do it this way than it does to do it the mathematical way. But again, it's in the standards, so you have to be able to do this. So that's how it's done. I also need to show you how to find graphical analysis using it to find the component vectors, to find the x and y parts of a single vector drawn at an angle. This time you're just going to have one vector that you're starting with. You have a single vector that you're going to draw to scale at the correct angle on a coordinate plane, starting at the origin again. the component vectors are added to that to make the right triangle. Again, it's kind of going in reverse. When we did the resultants, we had something on the horizontal, something on the vertical, and then we completed the triangle by drawing the angled vector in. This time we're going to start with the angled vector, and then we're going to add the horizontal and vertical parts to it to make the triangle, working really backwards. The first area you draw starts at the origin of the coordinate plane and goes until it reaches the end of the original vector. And again, it doesn't matter. You could draw in the x part first, or you can draw the y part in first. I would recommend doing the x because it might make figuring out things a little bit easier. Though in this case, it's probably not as important because, again, you've already drawn in an angle. I guess it's a matter of making your triangle include that angle that would make your drawing easier to understand and interpret. Then that second arrow just connects the tip of the first arrow you drew to the end of the original vector. Again, you're making that right triangle. And again, in words, it may sound confusing. When you actually do it and draw it, it's a little more straightforward. So we're going to find the horizontal and vertical components of a displacement that's 5.5 kilometers and an angle of 40 degrees above horizontal. So we could go either side of this, but 40 degrees really suggests we're over here in the upper right-hand quadrant of the coordinate plane. So we're going to draw a vector in over here that would be 5.5 kilometers at 40 degrees above that x-axis. So we're going to start by making our drawing. And 1 centimeter is going to equal 1 kilometer in this case. 1 centimeter equals 1 kilometer. I need a 5.5 centimeter vector. So let me get my arrow tool. And let me draw that 5.5 centimeter line. Goes to right there. Now I got to put that 5.5 centimeter line on this at a 40 degree angle. So let me get my protractor set up. I'll line it up as best as possible. And since I can't see through this protractor, I'm just trying to line the zeros up with my X. I'm trying to line that 90 up with my Y to make sure that it's as good as I can get. Now I'm going to have to rotate this until I'm at 40 degrees. Wow, how lucky does that get? So that's what my vector looks like. That's where I'm starting. Now what I got to do is I've got to draw my arrows in to make the right triangle. And since this is the 40 degrees right here, I want to include that angle in my triangle. So instead of going up and then over, I'm going to go over then and up. Again, using this horizontal first because that would be the one that actually includes the 40 degree angle. So let me get my arrow tool changed to a dashed arrow. I've got one that will go to approximately here. And again, this is where estimation comes in and why this method has error in it. Again, going to the end of that first vector is about right there. And then I got to draw a vertical one to connect the end of this one to here. And again, I want this to be as vertical as possible, so I use my grid to kind of make sure I've done that. Because if I make it a little bit diagonal, it's going to be longer than what it's supposed to be. If I go that way, it's going to be shorter than what I need it to be if I go that way. There's all kind of places to introduce error into this. Once you've done that, you would just measure the lines. And again, mine's not going to allow me to put the ruler over top of things and measure it, so I'm just going to have to move my vectors. So this one is a little bit past 4.2, so maybe 4.23 if we want to be that picky about it. So basically we have gone 4.2 kilometers east. That's the direction my vector pointed. And we can get rid of this one, and now we'll measure the other one. Grab it, Bring it over here. Flip it horizontal, and again, we want to try to get as horizontal as possible. All kinds of ways to introduce error into this, there really are. That's why this method is not the best method to use if you want good, accurate results. And again, I think the mathematical one's quicker anyways. This looks like it's exactly 3.6. And that would be north because we were going upward. So my x component, my horizontal component, was 4.2 kilometers to the east. My vertical component was 3.6 kilometers to the north. Again, the things that I don't like about the graphical method is that you actually have to have rulers and protractors and coordinate planes or graph paper to do all this. If you don't have a ruler, you don't have a protractor, then you can't do it. It's why if I make you do graphical analysis in class, I'm printing out paper protractors because everybody in the room is going to need a protractor. I'm printing out paper rulers because everybody in the room needs to have a ruler to get it done. You have to have all these tools. You have to have graph paper. You have to have a coordinate plane in order to do graphical analysis. The mathematical way of doing it requires nothing but a calculator and a basic understanding of trig. I mean, you don't even have to have a coordinate plane. You don't have to draw scale drawings. You can just draw a triangle on a piece of paper and solve it because you're going to use your math to calculate the missing parts of the triangle, to find the parts that you need to know, which again is just going to make your life so much easier. Most students, once they figure out this mathematical method of doing it, never go back to graphical again. The trig you have to remember are the trig functions, sine, cosine, and tangent, SOHCAHTOA, or whatever it is that they teach you when you're learning it in school. I've always hated that because there are some soft vowel sounds that sound similar. Is it sock as an S-A-O or S-O-A? I have no idea. It's always bothered me, and I never learned it right that way, and I always had problems remembering it. I never remembered the trig functions until another physics teacher taught me the way he learned it. He learned it through a sentence as a mnemonic device, one that you'll remember forever once you've heard it the first time, that gives you all three of these. The mnemonic device goes like this. Some old hippie caught another hippie tripping on acid. Some old hippie, that's sine, caught another hippie, that's cosine, tripping on acid, that's tangent. Again, there's none of those weird vowel sounds. You don't have to worry about, are you pronouncing these things correctly or not? You don't have to worry about any of that. You just have to remember the sentence. Some old hippie caught another hippie tripping on acid, and you can remember all your trig functions. Define resultants. Again, summarize your vectors down to a single horizontal and vertical. You've got to get it down to that X and Y single component for each one. Draw those out, connecting them tip to tail, just like you do in the graphical method. Draw them as a right triangle, and then draw in that resultant using the dash line or whatever to connect those two vectors to one another. Then you'll use the Pythagorean theorem, a squared plus b squared equals c squared, to figure out what the magnitude of the hypotenuse is, what the length of it. Again, no rulers, just a calculator to find that magnitude. And then you'll use a trig function to figure out what the angle is. To do that, you'll divide the appropriate parts. So if I'm doing sine, some old hippie, it's opposite divided by hypotenuse. I divide those two numbers out, I get the decimal value. And then using your calculator, you can take the inverse sine, and it's just the second function or shift key on your calculator and the sine button. You take the inverse sine of that number, and it'll tell you what the angle is. So again, nothing but a calculator is all you need. And once you get the hang of this, it's real quick to do because there's no scale drawings to do. You just sketch it down on a piece of paper, you punch some buttons on a calculator, and it tells you everything you need to know. It eliminates a lot of the error in it as well. So a plane flies with a velocity of 275 meters due west. I drew that one in first. Again, oftentimes it's easier to start with the horizontal one because you may be able to interpret that angle a little bit better, especially if you're asked to go to a standard angle. And do I know if that 1 centimeter is 2.75 meters per second, whatever? No, none of that. I just drew an arrow and I put 275 meters per second on it. A strong wind blows south at 130 meters per second. So then from the tip of this one, I attach the tail of my next one, tip to tail. And I just draw an arrow down, put 130 on it. Again, these are not to scale because they don't have to be to scale. I just have to put the numbers in here and draw those vectors down. My resultant goes from the origin to where my drawing ends, right there. So that dashed black arrow, that is my resultant. Now to figure out the magnitude, it's Pythagorean theorem. A squared plus b squared equals c squared. Doesn't matter which one you call A, doesn't matter which one you call B because you're adding them together. So I can put 275 squared plus 130 squared equals c squared, or I can put 130 squared plus 275 squared equals c squared, doesn't matter. I did the 275 first. Added those up. I got 92,525. Now that is c squared. Don't forget you have to square root that now to get an actual value for that hypotenuse. So 304 meters per second is what the magnitude of that new vector, that resultant, is 304. Again, I didn't have to draw any scale drawings. I didn't have to do anything but punch some numbers in a calculator. And now I know how far this is. And it takes out all of the error involved with drawing those vectors to scale and making sure that they're connected perfectly and stuff like that. So much quicker, and there's so much less error in that process. Now to find this angle here, I always use sine because it's the first one, sum multiply. It's the opposite, the one that's not part of that angle, 130 meters per second, divided by the hypotenuse, 304, which is 0.4276, blah, 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 blah. The calculator fills up this display with numbers. These are oftentimes irrational numbers, and they go on forever. I'll just round these to 4 numbers after the decimal point just because. No real reason, just because. Now I got to turn that into an angle. And so the way I do that is hitting the inverse or second function or shift key on the calculator, however yours is labeled, and then the sine button, and then I put in this number, 0.4276. So inverse sine of 0.4276 is 25 degrees. So I now know that this angle here is 25 degrees. Again, no protractor, no worrying about, did I draw this right? Are my scales correct? That's what the angle is, 25 degrees when you have those sides. Quick and easy, if you ask me. That's why people tend to gravitate towards this method. In fact, teaching CP classes, specifically how to do the graphical analysis method, when students were struggling with it and getting frustrated with them, I would show them how to do it mathematically, and then they'd be off to the races. They'd have this stuff done in no time. So again, it's the way to do it if you can do it. Now, as far as angle is concerned, it's 304 meters per second. That's a given. You don't have to worry about that one. Angle, we oftentimes like to report these as a standard angle, so we know which direction it is. If I just say 25 degrees, that actually implies that it's north and east in this direction somewhere, and it's not. So we want to be able to describe what that angle really is, and the best way to do that is to consider the unit circle. Over here, this would be 180 degrees. So over here is 180 degrees. And we have gone 25 degrees past that. So it's 180 plus 25. And we would probably want to report this angle as 205 degrees. Again, that gives us a more accurate description of what direction that vector is pointing. Again, if we just say it's 25 degrees, it's over here. But if we say 205 degrees, we know exactly where that vector is and exactly which direction it's pointing. Saying 205 degrees implies it's to the south of west. It gives us a much more accurate description. You could say 25 degrees, but you would have to say 25 degrees below west or 25 degrees below 180, something like that. That standard angle just makes it tidy, if you ask me. Let's take a look at the mathematical method to find the x and y components. All right, this should say component. Find a component or find components. Find components, draw the vector on the coordinate plane starting at the origin, so whatever one you're given, draw it from the origin of a coordinate plane. Again, it doesn't really matter if you get the angles and the lengths correctly because scale isn't important for this. You're going to use math to figure everything out. Then you're going to sketch the x and y components in to make a right triangle. Use the trig functions to find each side of that triangle. Sine is always going to give you the opposite side of that angle. Cosine will always give you the adjacent side because, again, some old hippie caught another hippie tripping on acid. Sine is opposite over hypotenuse, so it's always going to give you the opposite side. And cosine is caught another hippie, so that's always going to give you the adjacent. Let's check the flip chart. My apologies. Sine is always going to give you the opposite side, the one that's opposite your angle, not part of the angle. Cosine is always going to give you the adjacent side, the one that's connected to the angle. Again, sounds more complicated than what it is. This graphical analysis method is the way to do it. It's quick and easy. Of mathematical analysis. The ball is thrown 30 degrees above the horizontal with a velocity of 15 meters per second. How fast is it traveling horizontally and vertically? We want to know how fast it's going on the x and how fast it's going on the y. Again, I start by drawing in the actual vector, and that's the black one. Doesn't matter what length it is because none of this has to be to scale, and it doesn't even matter if that's exactly 30 degrees because, again, none of this has to be to scale. All we have to know is what the length of it is. The length is 15 meters per second. But we have to know what the angle is. The angle is 30 degrees. We then make our triangle. Again, it's often best to start with the horizontal one. So I start with my arrow going this direction, ending at the tip of that one. And again, it doesn't matter how perfect you are this time. It doesn't matter what the actual length is. So it doesn't matter how perfect you are. And then you connect that one up to the end of your vector. Exactly the same way you draw it when you're doing the graphical analysis method, just you don't have to worry about how long it actually is and making them perfect and stuff. So I need to figure out those two parts. Again, sine is opposite over hypotenuse. So sine is going to give us the side that is opposite of the 30-degree angle, the one that's not part of the 30-degree angle. It's going to give us our y. So the sine of 30, the angle I have, is equal to y, the side that's opposite, over 15, what my hypotenuse is. Rearrange that to solve for y. Y is equal to the sine of 30 times 15. Sine 30 equals times 15 is 7.5 meters per second. So I know that that is 7.5 meters per second north or up. And either up or north, depending on what we're doing here. So throwing a ball up is probably the better way of describing that. And then to find this x side, I'm going to use cosine because this x side is adjacent. This x side is connected to the 30-degree angle, so it's an adjacent side. Adjacent over hypotenuse. So the cosine of 30, again, the angle I was given, is equal to x, the adjacent side, over 15, what the actual hypotenuse is. Rearrange that to solve for x. X is equal to the cosine of 30 times 15. So I punch this in the calculator as cosine 30 equals times 15. That way I'm not getting the cosine of 30 times 15. So cosine of 30 equals times 15. That will give me 13 meters per second. 13 meters per second, and this is to the right. So I've broken this one vector down into how fast it's going to the right and how fast it's going up. It's two components. Again, I think the mathematical method is the way to do it. It's much quicker, much easier. There's a lot less error involved, and the way to go. So just make sure you know your trig functions and how to use your calculator to find angles with sines, and you're good to go.